Good morning, everybody. Good morning, everybody. How did you get on with the tutorial sessions this past week? I'm guessing if the tutorial session that I was in, some of you are finding some of you electricals are finding the mechanical stuff a little tough. Some of the mechanicals are finding the electrical stuff a bit tough. So what I'm going to start with today is I'm just going to run through a couple of systems, one mechanical, one electrical, just to sort of help you along the way. The tutorial sheet that you're going to get today is an extension of what we did last week, but with the content that we're going to cover predominantly today. But what I've done on the tutorial sheet is I've given you a whole bunch of standard equations, both electrical and mechanical, to help you try and solve the problem. So you're not expected to know those equations, because we'll give them to you. Let's see if this is going to work. Right, today, like I said, we're going to just run through a couple more examples of modelling systems using differential equations. We're then going to look at this thing called the Laplace operator. You should be covering Laplace transforms in your mathematics course, either currently or you did them last year. We're not going to focus on the mathematics behind it. We are using it as a tool. And so you don't need to worry too much about having to solve Laplace transforms in this course. We are using it as a tool, which we'll come on to. And to be honest, it's relatively simple the way we're using them. And that's going to lead on to this thing called the transfer function, which we use in control through every step. It's the thing that we use to represent systems. It's the thing we use to design controllers. It's called a transfer function, and we're going to introduce that today. We'll look at standard forms of transfer functions, first order and second order transfer functions, which are used to represent systems. And that's what we're covering today. So, first step, system modelling. As we saw last week, the way to model a system is to determine the differential equation that relates to that system, okay, that represents that system, and how it changes with respect to time. Okay, that's the main focus of what or the goal of system modelling. Okay, they could be. In this course we're going to predominantly be talking about mechanical or electrical systems. Okay, but the thing is that there are standard equations for both of these. Okay, and the equations for them are essentially the same. Okay, they don't change that much. And in this course, while we're dealing with different sorts of systems, because the equations are the same, it doesn't matter. The mathematics behind it is exactly the same. Okay, so don't fret if you're presented with a mechanical system and we say this is the transfer function for this system, and you're on electrical and you go, oh no, I can't do it. You can do it. The maths is the same. Okay, so don't worry too much. And there are analogies that we can draw between electrical systems and mechanical systems. So if you're presented with an electrical system, okay, because there are analogies, you can, if you want to, you can convert that electrical system to a mechanical system and then solve it that way. But like I said, because the equations are the same, it doesn't matter what you're dealing with. Okay? So, let's look at a mechanical system. We covered this last week. We've got a mass spring damper system, and we want to relate the force and the displacement relationships, force represented by F and displacement represented by X. You have a spring generally in a system, okay, and the force related to a spring is the spring constant K multiplied by its displacement, okay. The further you stretch a spring, the greater the force, the returning force of that spring, which is F of S. We have a damper in systems, okay, a damper has a coefficient of C, and that's related to the velocity. Okay, so depending on how fast you're moving something, the force will increase. The greater the velocity of that thing. Okay, if there's no velocity, then there's no damping force. And then we have an inertial system, and that's basically Newton's second law. Force equals mass times acceleration, which is the ma there. Okay, and so a force due to inertia is mass times acceleration. Notice here I'm using the dot notation. Does everybody know what that is, yeah? A dot represents one one derivative with respect to time. Okay, so this is cx dot, okay, is basically c times dx over dt. And obviously here I've got mx double dot, and that's going to be m times d2 2x over dt squared. Okay, so that's the second derivative with respect to time of displacement. That's the first derivative with respect to time due to displacement. That's what that dot notation is. Okay, so I've got these three equations, and they're all related to some sort of mass spring damper system. And I can also apply those to rotational systems. We had them in the we had an example of that in the tutorial sheet you had last week. Okay, unfortunately you can't really see the bottom of the screen, but basically a force is a torque. Okay, the x displacement, okay, turns into a theta, a rotational, in a sense, a rotation. Okay, and mass here in this equation relates to your moment of inertia. For a rotating system, okay, instead of mass we use a moment of inertia, because with a rotating system it depends on where the mass is placed around that thing that's rotating. Okay, you've got mass far apart, you're going to have a greater moment of inertia if all the mass is centered around the point of rotation. Okay, so it's not just mass, it's to do with its displacement, and that's what the moment of inertia helps us to determine. And so if we apply these equations, we have a system here, mass spring damper system. We want to relate F and X. Okay, so here's our system. We have a mass with a spring constant K, a damper constant C. We've got a force being applied, and we're stating that the positive motion is to the left. X is positive that direction. And so we've got our inertia. Well, that's Newton's second law, mass times acceleration. Well, that's simple. These are the equations that we had previously. Damping is c times the velocity, and then the spring force is k times x. And Newton's second law says the sum of all these forces must equal mass times acceleration. Okay, so here we've got all the forces being applied, F, the damping force, and the spring force, and that must equal mass times acceleration. That's what Newton's second law tells us. Okay, and obviously this here is the inertial term. Okay, so all the forces adding to a system must equal mass times acceleration. And so what you can do here is if you move these two terms to this side, so all the x terms on one side, you end up with this equation. I don't know why the screen is not showing that at the bottom, but basically you've got m x double dot plus cx dot plus kx equals the force. Okay, we covered that last week, but just to go over it again. Inertial force is mx double dot, damping force is c times x dot, and then spring force is kx. And you end up with a second order differential equation, which is shown on the bottom here. If you go onto a Blackboard and print out the slides before the lecture, you should be able to see all the equations. Okay, well, what about an electrical system or an electronic system? Okay, well, let's look at the relationships. If you've got a capacitor, your equation for the voltage across that capacitor is the charge over the capacitance, or if you wanted to look at the current, it's 1 over the capacitance multiplied by the integral of the current with respect to time. Okay, that's the voltage across the capacitor. Again, you don't need to remember these equations that well. Resistor, obviously that's V equals IR. Okay, but if you want to look at in terms of charge, it's the resistance times the change in charge over the change in time, dq over dt. And if you've got an inductor in the system, then the voltage across that inductor is going to be the inductance, L, times by the second derivative of charge with respect to time. Or, if you want to look at it in terms of current, we're looking at L times the first derivative of current with respect to time. So those are the equations for a capacitor, a resistor, and an inductor. And an example of that would be a LCR circuit, where you've got an inductor, a capacitor, and a resistor. And we want to relate the input voltage to the current. So here's our circuit, here's our inductor, here's our capacitor, and here's our resistor. And we have the equations for each of those, okay, which we covered in the previous section. These are all relating to current. We don't need to worry about charge in this one because we don't need to relate voltage to charge. We're relating voltage to current. And so we can say that the input voltage, okay, is going to be the voltage across the inductor, the voltage across the capacitor, and the voltage across the resistor. Okay, so basically V in equals VL plus VR plus VC. And so we substitute in for VL, L di over dt. For the resistor, we substitute in IR, and then for the inductor, we substitute in 1 over C times the integral of I with respect to time. So again, down here, we have a second order system, because obviously here we've got a derivative with respect to time, and here we've got an integral with respect to time. So in terms of the number of steps, okay, this is 2 steps away from that, so we're a second order system. Okay, so those are 2 examples of systems where you end up with a differential equation that helps us to model those systems. Now, we're going to talk about something called the S domain. This is where we deal with Laplace transforms. Now, as you are aware, differential equations, these ones are relatively straightforward to deal with. They can be extremely difficult to deal with, okay? They are a pain. And so we use, in control, we use something called the S domain, where we change the way differential equations, we apply this term S, which is called the Laplace operator, to a differential equation, and that makes it an awful lot easier to deal with, because essentially S we can treat as a variable, and the equation holds, okay? And so this is this thing called the Laplace operator, S, okay, and it can help in terms of manipulation. And so using Laplace transforms, we can convert these linear differential equations to a simple algebraic equation. Now algebra, as I'm sure you're aware, is an awful lot easier to deal with than differential equations. So we use this Laplace operator to convert our equation with respect to time, the differential equation, to a way that we can nicely manipulate it, okay? And then we use Laplace transforms, the tables of Laplace transforms, to convert that equation back into the time domain if we want to look at the response, and we'll cover that next week. But this week, let's just look at converting from the time domain to the S domain, which is what we're going to do. Okay, and what this does is helps us look at the transient and steady state components of the solution, okay, which we can obtain. So how do we do it? Well, okay, the definition of a Laplace transform, bit of theory, okay, of a function, which we're calling f of t, so it's a function with respect to time, okay. Laplace transform of a function with respect to time, we denote that with a capital letter F, okay. So we've gone from a function with respect to time is a little f, a Laplace transform, or S domain function with respect to S is a big F, and that is defined as the integral of f of t times e to the power of st dt. Okay, it's all, like I said, this is the basic theory. But to be honest, you don't really need to worry too much about this equation, okay, because we use tables to convert between one and the other, and there are some simple rules that you can follow as well. But this thing that's important is this complex variable S is what we know as the Laplace operator, okay. And like I said, if you want to look at more details into the theory, then you can go to your maths notes, because it should all be in there. Like I said, either you're doing it currently or you did it last year, so depending on which module you're registered on for this course. But the things we use frequently in our control is when we're looking at derivatives. Obviously, we're dealing with differential equations. One of the features of differential equations is we have derivatives with respect to time, okay, for our systems. We had obviously damping is c times the first derivative with respect to time, mass times the second derivative, and then we've got the same in electrical systems. And what you can do with derivatives is basically you can replace the d over dt term with an s. So with the first derivative, you have an s times obviously capital X in this case, because our function x is with respect to time. Okay, so that was displacement. We're now converting to the s domain. So you use a capital X, and you just to get, obviously this is velocity dx over dt. To get that, it's s times x. For acceleration, which is the second derivative with respect to time, okay, you then multiply x by s squared. And then the third derivative, so this is the rate of acceleration in a sense, then obviously that's going to be multiplied by s cubed. So whenever you see a d by dt, you can replace that with s. That's essentially what's going on. Multiplication by s in the plus domain corresponds to differentiation in the time domain with respect to time. Okay? And so every time you can see a d by dt in the differential equation of your system, you can replace by s. And obviously, whatever the derivative was, be that t or x or whatever, current, then you replace that by a capital X. And this time, that's capital denotes that it's a function of the s domain as opposed to the time domain. What about if we go the other way? Let's look at integrals. Okay, well, there's the basic rule. D by dt, obviously that's to the power of n. There's going to be s to the power of n times by x. Okay. What about integrals? Well, integrals in the time domain are converted to the s domain. And essentially, if you took an integral here, we've got 0 to some value infinity. Okay? Essentially what you do is you divide by s, and then we've got this term here, which is our constant of integration. And very, very frequently, almost universally, this term is 0, between 0 and 0. Okay? And so, essentially, to get an integral, you divide by s. Okay? So every time you see a d by dt, you multiply by s. Okay? And then you have a capital letter here. Here is our function. Okay? And if you see an integral, you have to divide by s. Okay? If there's two integrals, you integrate twice, then you obviously divide by s squared. Okay, so straightforward. D by dt, multiply by s, integrate, divide by s. And so, let's look at an example. We'll go back to that mechanical one. Okay, so there's our mass spring damper system. Again, I've called it ft now, little ft, and I've got xt is our displacement with respect to time. Okay, when initial conditions are 0, we have our differential equation. This is what we saw before. So mass times acceleration plus c times velocity plus k times displacement is the force. Okay, and what we can do is every time we've seen a d by dt, we've replaced it with an s times big X. Okay, so we've got s squared times by xs. Okay, and then we've got cs, because there's only one d by dt here. Okay, so we just have a 1s. And here there's no d by dt, so it's just k times big X. Okay, because there's no derivative, there's no s in this term here. Okay, and then obviously function of time turns into a function with respect to s in the s domain. So that's a simple conversion between a differential equation to the s domain. Okay, we've gone from this time domain equation, which is horrible to solve, second order differential equation, okay, to this nice algebraic equation. And you can see that this bit here is just a quadratic equation in terms of s. Yeah? And we can all solve quadratic equations. That's GCSE level maths. Okay? If we look at an electrical example, let's go back to that LCR circuit that we looked at before. Here I've got a voltage with respect to time and a current that will change with respect to time. And we determine the equation using these formulae. There's our equation. Okay, so here I have a d by dt. Okay, when we're talking about current, so what's that going to be? L times S times I of S, yeah? Capital I of S. Here I've just got I times R, so is there any S term in this one? No. Okay, it's just going to be I of S times R. And here I've got 1 over c times the integral of I with respect to time. So what am I going to have here? I'm going to have 1 over c, because that's obviously a constant, multiplied by what? I, S over S, yeah? It's going to be S on the bottom, So we end up with a situation that looks like this. LSI, as I said, you've got a d by dt here. So you have an s there. Here there's no d by dt, so you just have those two terms multiplied together. And then here we've got an integral, so you have an s on the bottom. You divide it by s. And again, that's a second order differential equation, represented now as a nice algebraic equation with s as a term. So that's the basics. Those are the things we need to learn predominantly. When you've got a derivative or d by dt, what do you do with the s's? And if you've got an integral, what do you do with the s's? Now we use these things in something called a transfer function, okay, which is a block on our block diagrams. We're covering block diagrams in a few weeks' time, okay. And the transfer function is there to represent the input and output relationship for a system or a component, okay. Every system that we talk about, any system that requires control, we looked at some examples last week, there's going to be an input and an output, okay? Sometimes there'll be multiple inputs and multiple outputs. We're not doing that just yet, okay? We're going to look at single input, single output systems, okay? And what we do is we represent a system with a block, okay? And that block is going to contain the equation of motion, or the equations relating to that system, okay? And so here's our block, here's our system. So let's look at the cruise control example that we had with the car last week. Okay, so here we've got our input, which is our throttle position, okay. This is the car, represented by an equation, and the output is going to be our speed, as an example, okay. Another example would be the furnace. Here we've got the fuel flow in, there we've got the furnace, okay, and there we've got the heat output. So that block is representing our system. There's loads of other examples. Let's think of an aeroplane with its flaps and ailerons, okay? Here we've got the control input from the pilot. There we've got the system that represents the flap, and there we've got the flap position as the output. Okay, the turntable, our voltage input from the potentiometer, our input speed, our system representing the turntable, the output speed. Okay, every system has got this sort of input-output relationship. And the thing that sits in the middle is called the transfer function. Okay, and that transfer function represents the system you are trying to model. And so we came up with those equations in the time domain. This time we've got them in the s domain. And what you do is you basically plot that equation into here. Okay, and that's going to be your transfer function. And what this does, any term in here, you take r, you multiply it by g of s, and you get c of s. So essentially it's a multiplication that's going on here. Okay, so c of s equals g of s times r of s. R of s is your input, g of s is the transfer function, and c of s is your output. And so we can say that the transfer function, what we do is we take this equation and we divide both sides by r of s, our input. And so the transfer function is the output divided by the input, and that's our g of s. Okay? Output divided by input. Don't get this modelled up. Output over input. Perhaps the best thing to do is to look at some examples. Let's go back to that tank example that we had in the last lecture and on the tutorial sheet. It's a single order system, okay? We said that last week that the flow into a system minus the flow out of the system is going to be the rate of accumulation of volume in the tank. And we said, we came up with the equation Q in, okay? This is the rate of volume accumulation in the tank. So there's a change in height over the change in times by the constant cross-sectional area of the tank, plus K times H, which is what we said is the flow out, okay? Q out is, we said, is some constant multiplied by the height, okay? And so we end up with an equation relating the flow in to the height in the tank. Now we can convert this to the S domain, okay? So I've replaced little q in with big Q in, okay? Capital Q, because we're now dealing in the S domain. Obviously, we've got a dh over dt. We've got a d by dt in there, so we multiply that h term by s. So we have a hs. And then obviously this term, there's no d by dt, so there's no s term. And so that's just k times h. Now you can see in the first line of this equation, there are hs terms in both of those terms. So we can multiply that out. We have as upon k. We can then divide both sides by h of s. So we end up with the input over the output, which is not the way we want it. And so we flip it upside down and we end up with 1 over k plus as. And then what I've done here is I've multiplied the top and the bottom by 1 over k. And so that this term drops to 1. And then we have a upon k, and then obviously this term becomes 1 upon k, which I've stuck outside, because that matches the standard form. Does that make sense? So we've gone from our differential equation to the s term, or the equation with respect to s, and then I've done a bit of algebraic manipulation, okay, to get to this form here, which is a transfer function. We have here our output, h of s, the height with respect to the input, which is the flow into the tank. Okay? Height over flow into the tank. And this is our transfer function that represents that equation. So if we went back, okay, here's our input, which is the flow into the tank. There's our output, which is the height, h, okay? And in there would be that equation, which is the transfer function representing that system. Okay? You multiply the input, which is the flow into the tank, by that transfer function, you'll get the output. Okay, so this is our transfer function for the tank system. Okay, so you can see, this is what we were doing last week, developing a differential equation to represent the system. Now this week, I'm sure you can imagine, your tutorial sheet is going to be going from this to this. Okay, transfer functions, getting transfer functions from the equation relating to that system. And so let's look at the mass spring damper system, a mechanical system. We determined our S domain equation beforehand, didn't we? Okay, that was the example that I used to show how to convert one equation to the S domain. Well, there it is again. And again, you can see that in the first line, there's an x of s term in each of those, so we can take that out. We end up with this, ms squared plus cs plus k. Nice quadratic equation, multiplied by x of s equals f of s. I've then divided both sides by x of s. So here I've got it the wrong way around. I've got my input on top and my output on the bottom. Obviously, I then have to flip it upside down to get the output upon the input, and end up with 1 over this quadratic equation. Okay? And what I've done here is I've multiplied again by 1 upon k, because I wanted a 1 here. And so I've got 1 upon k is this term here, and I've got 1 plus c upon k s plus m upon k times s squared. Okay? Because obviously I've divided the top and bottom by k, so this becomes m upon k, c upon k, and obviously k upon k is 1, which is what's going on down here. So that's the mass spring damper system, and here is my transfer function for that system. My output is x, my input is f. Okay, so if I had an f coming into my block, I had this equation in the block, the output would be x. Okay, that's how it works. Because you can see if you multiply both sides by f, you have f times this transfer function equals x. Okay. What about our LCR example? Okay, well we came up with that equation previously for the inductor, capacitor, resistor circuit. Okay, so again I see in this equation there's an I of s in each of these terms, so I can take that out. Okay. So we end up with Ls plus R plus 1 over Cs. Okay. And so what I've done is I've then divided by that. Okay, and then I've flipped them upside down, so I end up with 1 upon this equation. This isn't, like I said, this isn't in standard form. Okay, we want a 1 somewhere in here. And so what I've done is I've multiplied top and bottom by C of S. So I've multiplied C of S over C of S, which is obviously multiplying that equation by 1. But by doing C of S upon C of S, I end up with this term becoming C of S. Obviously this will become C L times S. This will become RCS, and this obviously is going to be CS upon CS, which is 1, okay? So I end up with this equation down here, C of S upon 1 plus RCS CS plus LC squared, S squared, okay? And this is our output over our input. Our input was the voltage, our output was the current. And so if we multiply this term, which is our transfer function, by the input, we get the output. And so again, this is our transfer function that we can stick in that block, and we then have our system represented, okay? Because we have our input and our output, and the transfer function which represents the system. Are there any questions at this point? Okay, I know this can be a little, like I said, a bit abstract. This is what I was talking about last week, where this is not a course you can cruise, okay? Because some of these concepts take a little bit of thinking about to really sort of understand what's going on and why we can do this, okay? Because you're thinking, okay, well, this was a differential equation up there, okay, but now we're dealing with it algebraically. What's going on, okay? Well, that's the beauty and benefit of using this Laplace operator, because essentially we've converted that to a nice algebraic equation, which we can then manipulate algebraically. And all we're doing is we're taking that equation and then setting the input and the output to be to give us this result, which is our transfer function, okay? So, like I said, the point of the tutorial sheet this week is to determine that equation and then get to this point, okay? So it's the next step. Now, as I was going through these last few slides, I was talking about standard form, okay? And, you know, I was talking about, let's get 1 here, okay? And that's because there are certain standard forms that we use for transfer functions because they tell us some characteristics of the way that system is going to behave, okay? You know, from certain types of responses, we could just look at the equation in standard form and we can make certain judgments about that system. And like I said, we're going to cover that next week in more detail. But the standard form is quite nice if you can set your system up to be in standard form, because like I said, from that, straight away you can make some judgments about how that system will behave in response to, say, a step input or a ramp input or something like that. Okay, so what I'm going to do is I'm just going to run through what standard form is going to be. So when you've got a first order system, like our tank example is a first order system, okay, this is the standard form. C is always going to be the output, R is always going to be the input, and we have this standard form. We've got gamma times by 1 upon 1 plus tau s, okay? So, I mean, obviously the other format would be gamma on top and then over on the bottom 1 plus tau s. And these gamma and tau terms represent certain characteristics of the system. Gamma is what we know as the gain, and tau is what we call the time constant. And the time constant will give us an indication of the way the system will respond to something like a step input, okay? A step input is where you're running along, you know, let's think of the furnace, okay? The furnace is off. You suddenly give it some fuel flow and ignite the fuel, and the system will respond, okay? Or we have our tank, it's empty of water, but, you know, so it doesn't matter what the valve is set on the output, okay? We start pouring in flow, okay? And obviously the height is going to rise. And so that time constant will give us an indication of how quickly, okay, our input matches our output. And so with the tank example, let's look at the equation. We came up with this equation in standard form, 1 upon k times 1 over a over k times s. So you can see instantly from this standard form that the gain is 1 upon k, so it depends on that constant, okay? And the time constant is going to be the area divided by that k term. Because if you think about it, okay, the k term was representing the flow out of the tank. If you remember, the flow out of the tank was k times h, okay? And the area of the tank, obviously that's, you know, the bigger the tank, the slower. If you imagine you had a huge tank and you started pouring water in from a pipette, it's going to take ages for the tank to fill up with water, okay? If you had a very small area, like a test tube, and you started filling up with a pipette, obviously the rate will be greater. So here we've got an A term on the bottom, And you can see that the k term, which relates to the flow out of the tank, okay, also is a indication of how that system will respond. Because the bigger the k term, the faster the flow out of the tank. Okay, then you can see just by inspection that makes sense. Yeah. If you have a big area, it's going to take a long time for the height to build up. And you see that A is on the bottom of this equation. Well, obviously, if you divide that by k, you get the time constant. And that's a representation of a first-order system in standard form. And so, as I said, the gain will be 1 upon k, and our time constant is A upon k. Now, in the second-order system, let's look at the mass spring damper. Okay, let's first off look at the standard form for a second-order system. Again, we've got this gamma term, which is our gain. And then we have 1 plus this term, 2 times, this is called the damping coefficient, over omega n, which is what we know as the natural frequency. And then we've got s squared upon the natural frequency squared. And so with our, like I said, this is the undamped natural frequency measured in radians per second. That's the damping ratio. It's a ratio of 2 terms, okay? And obviously the units for those 2 terms are the same. And so we end up with 0 or nothing as the units. And then the gain is obviously this term gamma. So looking at our mass spring damper system as the example, we end up with this equation, you remember? 1 upon k times 1 over 1 plus c upon k times s plus m upon k times s squared. And so you can see that our gain in this situation is 1 upon k. That's simple to deal with. If we said c upon k is going to be, c upon k was, if you remember, was 2 times this divided by omega n. Well, we end up with this term here if you do the algebra. And obviously our omega n, you remember there was it was s squared upon omega n squared, and so omega n must be root k upon m, which is the undamped natural frequency of that system. Okay? So we've gone from our mass spring damper system, okay, by using the Laplace transform and the S operator, we've developed a transfer function to represent that system. And then directly from converting that system into standard form, we can see from that system the natural frequency of vibration. So you've got a system that's going to be oscillating. Well, that's the natural frequency. Okay, we know it's an oscillating system with a damper, so we know there's going to be some damping. So it's going to be slowing down the damping coefficient. We can determine from this equation. And the gain, okay, which relates the input to the output, depends on purely just the spring constant. Okay. So by representing these transfer functions in the standard form, we can make judgments about that system, which really help us in terms of determining the performance of that system in response to a control input, which is the whole point of a control system. Yeah, we need to understand what the system will do in response to a control input. Okay, and these equations will help us to determine what will happen to the output in response to the input. Okay, because this equation relates the input and the output together. And so the standard equations for mechanical and electrical systems will be supplied. Okay, so the things like the equation for the spring, the equation for the damper, the equation for the inertia, and your inductor, resistor, and capacitor, those equations will be supplied. Don't worry too much about whether or not you can remember them. And what we'll do is we use the Laplace operator S to simplify dealing with linear differential equations. Okay, so every time you see a d by dt, you stick an s term in there. Every time you see an integral, you divide it by s. Okay, d by dt, you multiply by s, integrate, you divide by s. If you've got a second derivative, it's going to be s squared. The third derivative, s cubed. Okay, so it's quite a simple transition from your differential equation that you developed last week to the S-domain equation, which is what this week is all about. And then what we do is you can do some manipulation. Now that we've got a nice algebraic equation, you manipulate it to get your output divided by your input. And that is going to be your transfer function. So that represents the input-output relationships. And like I said, don't forget the transfer function is always the output term over the input term. Because if you think about that block, that picture, okay, you had an input going into a block with an output, okay? And if you multiply by the input by the output, by the input by the transfer function, you get the output, okay? And so if you divide the input times by the transfer function divided by the output by the input, you end up getting the transfer function on its own. So input over output will give you the transfer function. And like I said, you can then do a little bit of manipulation. Once you've got that transfer function, if you can put it in standard form, that's great, because it gives you some idea of the performance of that system just by looking at the standard form. Okay. Now we'll look at those things next week. Like I said, that's going to be looking at transfer functions and seeing what terms relate to what and how they look in response to various types of inputs. And that will give us an idea of the performance of the system. And so this week in your tutorial sessions, we've now got tutorial sheet 2. Okay. The answers to tutorial sheet 1 are now online. So if you went to Blackboard, well, I can go to Blackboard in fact. This is the end of the lecture. Let's go to Blackboard. I can show you what we're doing. Yeah. So let's go to Blackboard. I'll log in myself. No, not timetable. We don't want to see my timetable. It's horrible. So if we come to Blackboard, come on. So you'll see under course materials for this course, we have lectures and tutorials. That's where the slides are. So those are the slides I've just used. There's the videos of the lecture. So at the end of today, you'll see whatever. Do you want? Yes. You'll see a video of the lecture today, later on today. But then under tutorial sheets, I've now put the solutions to that tutorial sheet up there. So you can click on that, and obviously this will download the PDF of the solutions. Okay, so there's our, if you remember the tank was this equation. There it was. There's the answer. Okay, all nice and simple to see. And tutorial sheet 2 is up there. And like I said, tutorial sheet 2 is going to be looking at, there's your standard equations. Like I said, I've provided them to you there. And then we've got some examples. And we've got to determine the equation and then the transfer function for those systems. And we've got a whole bunch of different systems here for you to look at. Okay, so thank you very much. Go to these tutorial sessions and we'll see you next week.